can upload it like a 3. Oh yeah, maybe you can record it or upload it to YouTube. That way you don't have to send like the video to us, individually. You can just upload it to YouTube and we can just view
So
it
what
through
I
there.
did was it's recording now.
Okay.
It's recording now. So we'll see what happens. There's a place to stop recording. So at the end of the lecture, I'll hit stop recording and then see what I get and see if I can forward that to you or see if it's available. I don't know how to save it. I've never recorded my lecture before.
Okay. From past classes, what my previous lecturers would do is they would record like the Zoom meeting like that you did, and then they would just upload it through YouTube, and then we just.
I know I need to find the file. I don't. I'll find
we'll see it after. Yeah.
Okay. Perfect.
Thank you.
Okay, but it's recording right now. All right. All right. Are there any other questions?
Yes. Can you go to homework 2, number 7?
Oh yeah, how jolly bodies denature DNA. I did go over that. How jolly bodies are they are RBC inclusions, red blood cell inclusions. They look like a really dark, perfectly round marble. Okay, they're black, and what they are when you see that, it's usually seen in patients who have had a splenectomy or other conditions, but basically they're composed of denatured DNA, and it's reportable. If you see how jolly bodies, it's reportable, and the provider would like to see that you noted those.
Okay, thank you.
Did that answer your question?
Yes, thank you.
You're welcome. Any other questions? Okay. Okay. All right, let's go ahead and get started. Hemoglobin and iron metabolism. Again, if there's anything that you have a question on, or if I go over something that you didn't understand, don't feel bad about asking me, okay? I won't have any problems with anybody asking questions, and I'll be more than happy to clarify any kind of issues that you have. So today, I'm going to go over hemoglobin and iron metabolism. Okay, red blood cells. They travel a lot. They travel long distances, and that's only within your body, 200 to 300 miles a day. So they put on a lot of distance. They're busy. They're constantly moving. The lifespan of a red blood cell, notice it's in red, is from the time it's released from the bone marrow to the time that it undergoes senescence, which is the next point, until it dies, is 120 days. Okay, you'll definitely be asked that. What's the lifespan of a CBC? What's the average size of a CBC? Anybody? Average size?
2 to 3 microns.
2 to 3 microns is what it's expected to pass through. Remember the sinusoids of the liver and the spleen. 2 to 3. So 2 to 3 microns is a good number that you memorized, but probably the bullet before that would tell you the size of an RBC.
Is it 7 to 8?
Correct. 7 to 8 microns. Okay. You'll be asked that again, just like what I asked. Okay. These RBCs, after 120 days or approximately, the red blood cell undergoes senescence or aging. It's going to start cell death. And at that point, approximately 1% of the cells are replaced. Okay, they're replaced by cells coming from, where are they coming from? Where are the new cells coming from?
Bone marrow.
From the bone marrow. Okay, so I want you guys to, and I make this analogy that red blood cells are produced in the bone marrow, and that's the factory. Okay, the factory is either working overtime, it's either working as scheduled, or it's not working at all. There's a condition where the factory is shut down, and that will give you a certain type of anemia, and I'll get into that in a later lecture. But the bone marrow is your factory. Okay, that's where everything is produced. Your bone marrow consists of two types of tissue, myeloid and erythroid cells. The myeloid cells are the cells which consist of your WBC precursors, which is your lymphocytes, your neutrophils, and your monocytes. Okay, and your platelets. Okay, the largest cell in the bone marrow is called the megakaryocyte. That is a cell, the precursor for your platelets, and then that's in relation to the erythroid precursors. And I went through the RBC maturation sequence. Okay, there are a lot of RBC precursors in the bone marrow. So that's your erythroid marrow. Okay, you got your myeloid marrow and your erythroid marrow. And the normal ratio, and I'll get into this later, is about 3 to 5 to 1. Okay, it's either 3 to 1 or up to 5 to 1. Okay, that's what the normal ME or the myeloid to erythroid ratio is. Okay, so I have a lot of analogies too. So one of the analogies I just mentioned, the bone marrow is like a factory. Okay, at the end of senescence, the RBCs eventually are consumed by the RES or the reticuloendothelial system. The reticuloendothelial system is also called the mononuclear phagocytic cell system. If you can think of, which consists of like the monocytes. Okay, monocytes float around in your blood, and the reticuloendothelial system, it's kind of like your waste management system or your garbage truck. So your macrophages, they go around and look for junk in your blood. They go around and see schistocytes or RBC fragments or even bacteria. That's why there's phagocytosis going on. They go around and pick up foreign bodies, things that are not supposed to be in your blood. So they go around your blood and just clean up your circulatory system. Well, at the end of 120 days, the reticuloendothelial system will collect the RBC remnants because these red blood cells have died. So they're going to die, they're going to disintegrate. So there's a lot of stroma hanging around. And also too, there's iron. So in addition to the stroma that the macrophages or the monocytes will take care of, there's iron in those red blood cells that needs to be taken up, and it's taken up by the RES system. So later on, and I'm going to say, like as I mentioned earlier, later on, I'm going to talk about where iron is stored. That I think that's in the next lecture. So you have the RES system, the reticuloendothelial system. Okay, it includes the mononuclear phagocytic cells. Again, it's kind of like to clean up the garbage trucks in your blood. Okay, hemoglobin. Hemoglobin is a protein, we all know that. And its primary function is to deliver and release oxygen to the tissue. And hemoglobin is also, it also has the function to remove carbon dioxide as it returns from the tissue. It takes carbon dioxide from the tissue on its way back to the lungs, and then you exhale carbon dioxide. So hemoglobin is a protein. It picks up oxygen and then delivers it to the tissue. Okay. Hemoglobin is 4 globin molecules. The oxygen molecule is right there. Oxygen is not a fixed part of the hemoglobin molecule. If you can think of oxygen as being just a passenger, it's a passenger of the hemoglobin molecule. It's like the Uber picks up the oxygen and delivers it to the tissue, oxygen gets off. Okay, so oxygen is not a permanent fixture of the hemoglobin molecule. What the permanent fixture of the hemoglobin molecule is iron, because the oxygen will bind to an iron molecule. Okay, oxygen is, like I said, is just a passenger. It's picked up in the lungs and it's delivered to the tissues. And hemoglobin consists of a protoporphyrin ring and 2 pairs of globin polypeptide chains. So 2 pairs of globin polypeptide chains means that there's 4 4 polypeptide chains in total, okay? In the middle of this, and it's not there, is iron. And it's the iron that binds to the oxygen, okay, in the middle of this ring. And here's another picture of the hemoglobin molecule. And right there is your iron. This is where, and you can see that it's the Fe2 plus. Fe2 plus is the ferrous state, okay? Fe2 plus is the ferrous state. I always got this confused when I took chemistry, but I finally learned that Fe2 plus, you just have to memorize it, but I have a trick for you. Fe2 plus is the ferrous state and Fe3 plus is the ferric state. Okay, each heme residue contains one central coordinated bound iron atom that is normally in the Fe2 plus or ferrous state. Okay. And oxygen is carried by the heme proteins bound to the ferrous iron atom. So if you take a look at it, if it's not ferrous, the other form of iron is the Fe3 plus, and that's the ferric state, Ferric, and that's the Fe3 plus. To remember that the Fe2 plus or the ferrous iron is the one that binds to oxygen. You see that O there? If you see the O in ferrous, that means that's the one that will bind to oxygen. If you don't see the O, like as in ferric, that's the one that will not bind to oxygen. Okay, so just so you can remember that the Fe2 plus or the ferrous iron is the one that will bind to oxygen. Okay, so remember that trick. Okay, 4 globin chains in the adult, even in the infants. For the adult, you got 2 alpha, alpha 1, alpha 2 globin chains, and the beta 1, beta 2. Okay, so you got alpha 1, alpha 2, and there's your heme group. The heme group consists of iron and oxygen. Okay, iron and oxygen, that's your heme group. So hemoglobin, normal hemoglobin production depends on 3 processes: iron delivery and supply, the synthesis of protoporphyrins, and adequate globin synthesis. That's normal hemoglobin production. It's dependent upon other things too. Okay, like for example, the big thing is need. Okay, the need for blood, and there's certain situations that'll be very apparent to you in examples that I'll be discussing later. Okay, so iron in the ferric state. Okay, do you see an O? No, you don't see an O. So Fe3 plus does not like to bind to oxygen. It's bound to CO2, and since it's bound to CO2, that means it's hemoglobin on its way back to the lungs so it can unload the CO2 in the lungs. And at that point, it's converted to the ferrous state, where it's gonna pick up oxygen and be on its way to the tissues. So hemoglobin is actually in 2 forms. Okay, hemoglobin is, you got hemoglobin in your arteries, which is in the ferrous state because it contains oxygen, and the ferric and hemoglobin, which is in the ferric state, which contains CO2, is on its way back to your lungs. Do you see that? Hemoglobin is in 2 states, ferric and ferrous. I mean, the iron is in 2 states. Okay, so just remember that O in the ferrous is the Fe2 plus and contains oxygen. Okay. So iron is delivered to the membrane of the RBC precursor in the Fe3 plus by transferrin. Transferrin is another protein. Okay, so when it's in the ferric state, now we're getting in to delivering iron. It's not bound to any oxygen yet. What it's doing is it's taking iron from the reticular endothelial system and actually delivering. We're not talking about oxygen delivery now. We're talking about iron. Iron that has been released from dead red blood cells and taken up by transferrin from the reticular endothelial system back to the bone marrow. And there's a pretty good illustration of that later on. And it shows where iron is picked up at the end of the red cell life. Transferrin picks it up and delivers it to your bone marrow, and then that's where you produce your red blood cells. Okay, so excess iron aggregates. Excess iron, if it's not being used, it still has to be bound to a protein. And iron aggregates in the form of ferritin. Okay, 2/3 of the total body iron is bound to heme in the hemoglobin molecule. The total body iron is bound to heme in the hemoglobin molecule. The important thing to note is that iron cannot be free, okay, because free iron in the blood is toxic. Your body, if it'll detect free iron, it'll filter it out and it'll end up in your liver. All right, hemoglobin, as I said, consists of 4 chains, 2 alpha chains and 2 beta chains. Those are your 4 heme groups in the adult hemoglobin. The alpha chain consists of 141 amino acids, and the non-alpha chains. Now, I could have said, well, beta chains, but there's other non-alpha chains like gamma. There's a gamma chain, and there could be like a delta chain. Okay, the more common non-alpha is gamma, but non-alpha chains have 146 amino acids, and the sequence of amino acids is different for each chain. One interesting thing about hemoglobin is very, very similar to chlorophyll in plants, with the exception of the metal in the middle here. In humans, it's iron, and in plants, we have magnesium ion there. So you can see that heme molecule is very similar to the chlorophyll molecule. Okay, abnormal hemoglobins are carboxyhemoglobin, methemoglobin, and sulfmethemoglobin. Carboxyhemoglobin, oxygen molecules are replaced by carbon monoxide. Okay, so people intentionally or unintentionally poison themselves by carbon monoxide poisoning, and unintentionally meaning that when I was in Bremerton Station, Bremerton, you know, I would hear on the news, and it would happen a little bit more than rarely, meaning like occasionally, where people would, during the winter months, it would be really, really cold. They wouldn't have any heaters. So what would happen would be that they would bring in their barbecue and fire up the barbecue in their house, thinking that they're going to warm up the house. But what that is you're actually generating carbon monoxide. And they would actually end up, you know, families would end up killing themselves, unfortunately. So the thing about carbon monoxide, it's a very, very poisonous gas. What it'll do is oxygen will bind to the oxygen will bind to hemoglobin. However, carbon monoxide will replace oxygen and bind to hemoglobin much more tighter than the oxygen bond. So the affinity for carbon monoxide is 200 times greater. So in the presence of carbon monoxide, oxygen will be easily replaced 200 times greater. So it's a very toxic poison, and that's carboxyhemoglobin. Methemoglobin, we have methemoglobin in our blood right now, but it's not in very significant amounts that it's going to hurt you. However, whenever you're injured or if you're exposed to toxic agents, what will happen is you'll create an oxidant stress situation where your hemoglobin will be converted to methemoglobin, and it's going to cause oxidant stress. What happens when you're injured or you're exposed to these toxic agents is that the hemoglobin is oxidized. Remember, the ferrous iron contains oxygen, correct? In the presence of these toxic agents or injury, the ferrous iron is going to be converted to ferric. Okay, remember, the ferric iron does not contain oxygen, it contains CO2. So actually, all the iron in your blood in the presence of toxic agents, a significant amount of iron in your blood will be converted to the ferric form. So if it's already converted if it's already carrying oxygen, so ferrous iron contains oxygen, meaning that it's on its way to the tissues to be delivered, that iron that contains oxygen will be converted to ferric, okay? So what happens is at the tissue, it's not going to release oxygen, and that's the problem, okay? The ferrous iron that contains oxygen, as you know, when it's at the tissue, it's not going to release the iron. On the other hand, you got ferrous, ferric iron on its way back to the lungs in the 3+ form. When it unloads the CO2, it's not going to be converted to ferrous. It's going to stay in the ferric form, so it's not going to bind to oxygen. Hence that statement there, it cannot bind to oxygen. So in the lungs, it can't bind to oxygen. At the tissues, iron bound to oxygen is in the ferric form, so it's not going to release oxygen. So the problem with methemoglobin is that this type of hemoglobin will not deliver oxygen to the tissues. Okay, and that's the problem, and that's caused by oxidant stress, as opposed to antioxidant. Okay, and there's a disease, enzyme deficiency. I think you may or may not have heard, is G6PD deficiency, glucose 6-phosphate dehydrogenase. I'll get into that when I talk about the hemoglobinopathies. So what happens? So the bottom line, the take-home lesson on methemoglobin is that the hemoglobin will not deliver oxygen to the tissues, or it cannot bind to oxygen in the lungs. Okay, it's because it's in the ferric form. All ferrous iron has been converted to the Fe3+ form. All right, so oxygen cannot be picked up, nor can it be delivered to the tissues. And final abnormal hemoglobin is sulfmethemoglobin. It's a combination of hemoglobin and hydrogen sulfide. And this is an acquired hemoglobin, where you can get it from ingesting sulfur-containing drugs. When you have sulfmethemoglobin, the problem is you now have hemoglobin. If you take enough of these sulfur-containing drugs, your hemoglobin now is incapable of carrying oxygen. Well, if you're not capable of carrying oxygen, you're not going to be delivering, and becomes an incompatible with life situation. Okay, unfortunately, with sulfmethemoglobin, it's not reversible. So if you take sulfur drugs, usually if you take a drug and it creates a problem, the remedy would be to take away the use of the drug. Well, in this case, ingestion of sulfur-containing drugs, if you find out that you're creating sulfhemoglobin, it's not reversible. It's not as easy as stop taking the sulfur drugs and it's going to go away. Okay, so it creates a hemoglobin that's incapable of carrying oxygen, and it's not reversible. Okay, types of hemoglobin. The breakdown of hemoglobin in your blood now is 95 to 97% hemoglobin A. A lesser percentage is 2 to 3% hemoglobin A2, and to a lesser extent, 1 to 2% is hemoglobin F. Hemoglobin F is your fetal hemoglobin. Okay, is your fetal hemoglobin, but your normal adult hemoglobin is hemoglobin A. So hemoglobin F, your fetal hemoglobin, consists of alpha and gamma chains. Adult hemoglobin consists of alpha and beta chains. So fetal hemoglobin is alpha 2, gamma 2, 2 alpha chains and 2 gamma chains. So normally, in utero and at birth, your hemoglobin is predominantly hemoglobin F. And what happens is, after birth, your hemoglobin F will gradually convert over to hemoglobin A, and eventually be approximately 2%. So the hemoglobin F will go away and hemoglobin A will take over. The production of hemoglobin F normally takes place in areas other than the bone marrow. Okay, in those locations other than the bone marrow, there's a specific term. Do you know what that is? Other than the bone marrow, outside of the bone marrow, like production outside of the bone marrow. Anybody know? Okay, it's called extramedullary hematopoiesis. Extramedullary hematopoiesis. Okay, extra, let's take a look at extramedullary. Extra means outside, okay? Extra meaning it's outside. Like, for example, if you have a line that goes up 45 degrees and then it tapers off, then the area that continues on at 45 degrees is called extralinear. Well, extralinear is assuming that it stayed at 45 degrees, but in reality, it tapers off. That's what happens with a growth curve. It doesn't stay at 45 degrees. It'll taper off and actually create a plateau. So at the point where it starts becoming a plateau, if you continue on at 45 degrees, that's the extralinear portion. In other words, it's outside the normal growth line. So it's outside. In extramedullary, the two types of, let me see, let me go to this, right here. Okay. Ignore the rest of this, but here's a bone right here. Okay, the inside of the bone is called the marrow, or the medulla. This is the medullary part of the bone. The outside part of the bone is called the cortex. Okay, so the outside of the bone is called the cortex or cortical. If you see the term cortical, then that means, oh, it's the outside of something. Just like the brain, the cortex of the brain is the outside of the brain. The medulla is what's inside of your brain. Just like in the bone, this is the medullary part of the bone. It's where the marrow is, okay? So extramedullary means outside of the bone marrow. So there's production of blood outside of the medulla of the bone. And those areas where there's hematopoiesis that takes place is the spleen, thymus, lymph nodes, and the liver. Hematopoiesis actually takes place in these areas. You'll be asked that, by the way. What are some extramedullary locations? And you'll answer spleen, thymus, lymph nodes, and liver. Okay, now getting into iron. Iron metabolism. Iron is an important element in the function of all cells. Like I mentioned earlier, your body has to protect itself from free iron because it's toxic. Okay, your body doesn't like free iron. It has to be bound to a protein like ferritin or transferrin or hemosiderin. Okay, free iron is deposited, again, free iron as a toxic material is deposited in the liver where it can cause damage to the mitochondria and lead to necrosis of hepatocytes. Hepatocytes are liver cells. So the main role of iron is to carry oxygen. Remember, to carry oxygen, it has to be in the Fe2+ or the ferrous form of iron as part of hemoglobin, and the ferric form to carry carbon dioxide to release it in the lungs. So the main role of oxygen is to carry iron. So here, this is iron metabolism. Here we have bone, you have circulating RBCs, and this is the reticuloendothelial portion of this cycle. So the erythroid bone marrow, inside the marrow, like I said, are erythroid precursors. The erythroid marrow. This is like, remember the RBC maturation, everything before reticulocytes, remember the orthonormochromic erythroblasts, et cetera, et cetera. This is the erythroid marrow. This contains the erythroid precursors. Those precursors, those nucleated red blood cells will never, well, maybe some NRBCs will never reach the peripheral circulation. So this is the factory part of your red blood cells. So what happens is this is where red blood cells are formed. Okay, and what it is, it's taking transferrin that is carrying iron from the reticuloendothelial stores. So let's start over here. It receives iron from transferrin into your erythroid marrow. Okay, iron goes to your erythroid marrow, goes to the factory, and the factory will produce red blood cells. Okay, the factory will produce red blood cells. After 120 days, these red blood cells will start aging, will start dying, and start shriveling up, and the iron will be consumed, the stroma or the skin of the red blood cells will be cleaned up by the macrophages and the monocytes, and the iron will be bound as ferritin in the reticuloendothelial storage. This is your storage area. This is where iron will be stored. Okay, and what will happen is it'll take iron from the stores whenever there's a need, and the need is going to be depend on the marrow saying, I need more iron. The transferrin, what will happen is it'll take iron from reticuloendothelial stores, take them from there, and transfer it over to the erythroid marrow. Now, this is not the only place where iron is needed. Iron will be needed in the liver, and the iron will also be needed in the gut, and iron will also be needed in extravascular exchange. But mainly, the majority of the iron is to take it from the reticuloendothelial stores and send it to the erythroid marrow. It's that important. It's important because this is where you're going to produce your red blood cells. Okay. So whenever there's a need, like for example, a gunshot wound, or if you got into a car accident and you're bleeding blood all over the place, this marrow is going to become active and say, I need more iron. I need more iron so I can produce more red blood cells. I'm going to get into that cycle in a minute, but this is the normal cycle. Transferrin will take iron from the reticuloendothelial stores and either send it to the gut, extravascular exchange, or the liver. But for the most part, for your daily needs, it's going to send it to your bone marrow, specifically your erythroid marrow. Okay, so the erythroid marrow will take the iron from here, and send it and produce. It'll go into production to create your red blood cells. Okay, and that's how hemoglobin is formed. That's how your red blood cells are formed. 120 days, it's going to die again. Hemoglobin collected, iron stored, iron picked up by transferrin and sent back to the erythroid marrow. Okay, so that's your cycle. That's the cycle of, well, it's not the cycle of, I mean, obviously you have 120 days here, but this transferrin is picking up iron and delivering it, picking up iron and delivering it, okay, either to the liver, extravascular, or to the gut. Okay, but this is a cycle of iron, your iron metabolism. Okay, keep that in mind. Remember that the meroid, and this is medullary hematopoiesis now, as opposed to extramedullary. This is in the medulla now, medulla of the bone. Okay. Transferrin, that's this guy right here, transferrin. Transferrin carries iron and exists in two forms, monoferric and diferric, one iron or two irons. Okay. The normal turnover, a half clearance time, is very rapid, 60 to 90 minutes. So from here to here, picking up and delivering is an hour to an hour and a half, 60 to 90 minutes. All right. 60 to 90 minutes is turnover, pickup and delivery to the bone marrow. So most iron transported by transferrin is delivered to the erythroid marrow. You already know that. I just explained it. It's picked up from the RE cells and delivered to the erythroid marrow. The clearance time is affected mostly by the plasma iron level and the erythroid marrow activity. Actually, the plasma iron level will dictate what the erythroid marrow activity will be. So what I mean is plasma iron levels. Say, for example, you get into a car accident, you got stabbed or shot, you're going to be bleeding all over the place. So you're losing blood. Therefore, you need to replace the blood that you lost. Okay, therefore, you have plasma iron level that's in demand. Okay, it's in demand. So if it's in demand, then your factory is going to crank up production. Your factory is going to crank up production. Okay, so what happens is erythropoiesis is stimulated. Erythropoiesis is the production of red blood cells. It's now stimulated because of the car accident, because of the gunshot wound or stabbing. You lose all that blood. Your body is smart. It's going to want to replace that blood by increased production of erythropoiesis in the bone marrow. Okay, therefore, the pool of iron requiring erythroid cells will increase. The iron requiring erythroid cells are the erythroid portion of the bone marrow. Those are the erythroid cells of the bone marrow. It's going to tell those erythroid cells, hey, you guys need to go to work. You guys are going to overtime now because we need to crank out RBCs. Okay. The clearance time. Remember the clearance and the turnover, the pickup and delivery of transferrin from the RE to the erythroid marrow. That is, remember the normal turnover time. Anybody remember? It's an hour to an hour and a half from pickup from the marrow. Pickup from the reticular endothelial cells to the bone marrow is an hour to an hour and a half. When there's a need, when erythropoiesis is stimulated because you have been into an accident or stabbed or shot, you need to make more blood. Your turnover is no longer 60 to 90 minutes, but it may be as short as 10 to 15 minutes. So you know what I'm talking about. So this cycle here, pickup and delivery, 60 to 90 minutes is no longer 69. It's now 10 to 15 minutes. Okay. You guys follow me so far?
Yes.
Okay. So it's no longer 60 to 90 minutes. You have an incredible need. Turnover is now cranked up to 10 to 15 minutes. Okay. Just like a factory, you're telling them to work overtime. Okay, on the other hand, suppression of erythropoiesis. So let's say that your body's good and they already transfuse enough blood into your circulation, and you're fine. Your hemoglobin is back up to normal level, maybe 13, 14 grams. You don't need to crank up your bone marrow to make more blood because your hemoglobin level is fine. So you need to suppress erythropoiesis, and you don't want that. So you don't want that to stop. And your body should know that while my hemoglobin is fine now, I don't need to have increased production of red blood cells. So what will happen is the plasma iron, if you don't stop or it slows down, it doesn't slow down enough, the plasma iron level will actually increase, and the half clearance time may be prolonged to several hours. So instead of 60 to 90 minutes, it's gonna be increased to maybe 120 to 150 minutes. So the clearance time has to slow down, and your iron level will actually go up. Okay, because that iron that's normally picked up from the RE system by transferrin and delivered to the bone marrow, it doesn't need to go to the bone marrow anymore because you have enough red blood cells. You've already recovered from your blood loss. Therefore, your iron level is going to increase. Okay. So normal turnover is 10 to 20 times per day. And with a normal plasma iron of 80 to 100, the amount of iron passing through the transferrin pool is 20 to 24 milligrams per deciliter. Those last few points on the turnover and the normal plasma iron, etc., you notice it's not red, so you make just information for you to digest. Okay, that's it for iron metabolism. Now, iron deficiency. For me personally, iron deficiency anemia is one of my favorite anemias because it's really easy. Hopefully it's going to be easy for you to identify. Okay, iron deficiency anemia. It's the most prevalent form of malnutrition, and that's what causes it. And globally, half of the anemias in the world is attributed to iron deficiency anemia. This is probably an old number, but 841,000 deaths annually worldwide due to iron deficiency anemia. There are three stages of iron deficiency anemia. First is negative iron balance, followed by iron-deficient erythropoiesis. Now the bone marrow is starting to get involved. So first one, negative iron balance, is due to diet, perhaps. The next one is iron-deficient erythropoiesis. Again, erythropoiesis, when you see that, the bone marrow is starting to be involved in the second stage. And then finally, in the third stage, you have full-blown iron deficiency anemia. Okay. So negative iron balance. So negative iron balance can be as simple as the demands or the losses of iron. So you lose iron for whatever reason is greater than the amount of iron that you're replacing and that it's being replaced with. So conditions like blood loss, pregnancy, adolescent growth spurts, or poor diet can create a negative iron balance. So the demand or the need for iron, the iron loss is greater than the amount of iron that it's going to absorb. Okay, so that's the negative iron loss. And usually the iron is taken from the reticuloendothelial storage sites. You all know that from the diagram I showed you earlier. It's taken from the reticuloendothelial storage sites. So in negative iron balance, iron stores, and iron is stored in the reticuloendothelial site. That's where iron is stored. Okay, so your stores are decreased but not depleted. Iron stores are decreased but not depleted. Your serum iron and TIBC, the total iron binding capacity, are still at normal levels. So by doing chemistries, I mean, you can do an iron level. It may be a little bit low, but but the chemistry test, serum iron. So you draw blood, you're feeling a little tired, just a little bit tired. You draw iron and iron binding capacity, the TIBC. You're going to get normal levels, but your iron deficiency process has already started. Also, too, on the CBC end of it, the chemistry, your iron and iron binding is normal. In hematology, you draw a CBC, you're going to get normal RBC morphology, and your indices are normal. So you won't even be able to detect a normal iron balance from lab work that's being collected. Okay, normal morphology in hematology, normal chemistries, normal iron and iron binding. Okay, it's negative iron balance. The next stage is iron-deficient erythropoiesis. So here, your iron stores are depleted. So iron that's stored in the reticuloendothelial systems has now been depleted. The transferrin has taken all of the iron from the RE cells and has taken it to your the bone marrow, but the stores are now depleted. Okay, the serum iron levels will also fall, and the total iron binding capacity and porphyrin levels will increase. So as long as the serum iron level remains within normal range, hemoglobin synthesis will not take place. It's only when the iron levels fall out of normal range that hemoglobin synthesis will be turned on. Okay, if the iron, so I'll say it again, if your iron levels are normal, then hemoglobin synthesis or hematopoiesis will not take place. It's only when the serum iron is abnormal or it's really, really low, that's when the hematopoiesis will take place. In this case, iron-deficient erythropoiesis, there's no more iron stored, so it's critically low. Finally, in iron-deficiency anemia, transferrin saturation falls to 15 to 20%. Normally, transferrin saturation can be up to 50%. I'll show that to you in a later slide, probably the next two slides. But transferrin saturation, meaning the iron that transferrin has picked up, it's only 15 to 20%. That's not very much. So if you think of iron as being a passenger of transferrin, you don't have very many passengers, in other words. Okay, transferrin saturation is 15 to 20%. So hemoglobin synthesis is impaired, and now you're going to start seeing microcytic cells, okay, because iron is low. Hemoglobin synthesis in the bone marrow is impaired, so now you're producing microcytic cells. What do microcytic cells look like? Anybody?
Small.
Small. So how can you detect that from a printout on a CBC printout?
Look at the MCV.
MCV, correct. MCV, it's one of the first things you look at, and that's why I want you guys to be familiar with looking at the RBC indices. The first thing you look at is to see if it's acceptable, and that's by looking at the MCHC. Like I said, if it's in the 40s, forget it. This is not a good sample. Next thing you look at, if the MCV is okay, then you take a look at other things. And one thing is to look at is the MCV. So to see what you're dealing with. There's a lot of things that you can pick up from looking at this MCV, and I'm going to teach that to you. So in iron deficiency anemia, the cells are microcytic, meaning that the cells are small. And also too, because this is an anemia, hemoglobin and hematocrit will begin to fall. So everything's low, low reds, low hemoglobin, low hematocrit, low MCV. Okay, those are your RBC indicators. Your reds, your hemoglobin, hematocrit, and your MCV. Your RBC indices too, like MCH and MCHC, but those are your measured parameters. Also too, in iron deficiency anemia, you're going to have moderate hemoglobin at 10 to 13, but it's going to get worse. Your bone marrow is going to be hypoproliferative, meaning that there's going to be a lot of non-production. In highly productive bone marrow is going to be very hyperproliferative. That means very active bone marrow, a lot of cells in the bone marrow working. In iron deficiency anemia, you're going to have a hypoproliferative, means a low production, low producing bone marrow, a lot of white space. Okay, a lot of space in iron deficiency anemia. And then it'll progress into severe anemia, where your hemoglobin can be as low as 7 to 8. And then that when it's as low as 7 to 8 hemoglobin, this is the proper description of iron deficiency anemia. It's called a hypochromic microcytic anemia. Okay, hypomicro in short. It's a hypochromic, meaning that low hemoglobin in the cells, and microcytic, small cells. And since it's anemia, there's a lot of white space in the field. So and also too, there's a lot of POIC. You're going to see target cells. You're going to see teardrop cells. You're going to see schistocytes. Going to go over all these abnormal RBC forms. You're going to see the whole spectrum: target cells, macrocytes, microcytes. You're going to see schistocytes. You're going to see all kinds of things. Elliptocytes. You see the whole spectrum, and you'll see that in iron deficiency anemia. Another thing that will help you identify that you have iron deficiency anemia, on the CBC, there's a parameter called REW, which is the elevated is the random distribution width, and the REW is also very elevated. Okay, I don't know if I gave you the normal value, but if you get an RDW in the 20s, 20 to 25, that means you have a lot of variation in size. You have a lot of anisocytosis, and that's how you can tell the difference between another hypochromic microcytic anemia, which is thalassemia. It's also hypochromic microcytic, but the RDW is not that high. And so in iron deficiency anemia, the marrow is increasingly ineffective. So hence, you're producing all these abnormal red blood cells, and you're not getting enough iron. So serum iron and TIBC are related. Serum iron will represent the amount of circulating bound to transferrin. Okay, the iron that you're measured, serum iron, will tell you the amount of circulating iron that's actually bound to transferrin. And the total iron binding capacity is an indirect measurement of circulating transferrin. So the two are kind of related to each other. Normal ranges, as you can see, it's not in red, it's black. I'm going to reserve normal ranges for your chemistry class. Serum iron is 50 to 150 micrograms per deciliter. Total iron binding capacities 300 to 306. Transferrin saturation is 25 to 50%. So remember, in iron deficiency anemia, I think I said it was like 10 to 15 or 15 to 20. So transferrin saturation is 15 to 20, and normally it's 25 to 50%. Okay, so that's normal saturation. and that's transferrin when it picks up from the reticular endothelial cells, reticular endothelial system. So the saturation is normally 25 to 50%. So iron deficiency is associated when transferrin saturation levels are below 18%, and normally it's 25 to 50. So when the saturation level is below 18%, then now you have iron deficiency anemia. Okay, stored iron. Stored iron. Remember, iron is stored in the reticular endothelial system. Stored iron is complex to a protein known as ferritin, and that's in the RE system. The ferritin accumulates within the cells of the RE system, as I just said, and can aggregate. All this ferritin can aggregate. When you have these aggregates, they become hemosiderin. So in the reticular endothelial system, ferritin, iron-borne ferritin, will accumulate, and then when it aggregates, it forms hemosiderin. Okay, iron in ferritin or hemosiderin can be extracted by the RE cells. So it's stored in ferritin, and then when it's needed, it can be the reticular endothelial cells can extract it so that transferrin can take it out. Okay. Under steady conditions, serum ferritin levels correlate to the total by ferritin. So make sure you know that ferritin and storage go hand in hand. So iron is stored as ferritin in reticular endothelial cells. Okay, make sure you know that. Iron stored as ferritin in the reticular endothelial cells. So ferritin levels estimate iron stores. Okay, so I must have said it about 4 different times. Iron, ferritin storage, okay? Normal values, again, 100, for males, it's 100 micrograms, and females, not so much to be normal. They can be as low as 30 micrograms per liter. Serum ferritin below 15 micrograms means there's no body iron stores. No body iron stores. Okay, so here's some drawings of some red blood cells. You got normal red blood cells. I kind of don't like this, but I'd rather show you real cells. So normal red blood cells with your normal central pallor, macrocytic cells, large cells, microcytic cells, microcytic hypochromic. Those are your small cells, and large central pallor. Normocytic, normochromic, again, those are your normal cells, and hemolytic anemia. I'm going to talk about hemolytic anemia. It's another type of anemia. You'll see cells that have no central pallor, but in addition to that, you'll see what's called schistocytes. Okay, schistocytes are RBC fragments. So here you got spherocyte, no central pallor. Elliptocytes are oval or cigar shaped. Teardrop cells are dacryocyte. Schistocytes, this is misleading because it seems like it's the same size as these, but schistocytes as an RBC fragment is smaller than this. Echinocytes are spiny. Echino mean like a starfish, the spines on a starfish. Acanthocyte is irregular spikes, not its irregular location. It's kind of like echinocyte where, but the spikes are evenly distributed around the cell. For an acanthocyte, the spikes are fewer and irregularly placed on the red blood cell. Then you have your target cell and your stomatocyte. And this is supposed to be like a slit, or it looks like a mouth. Okay, and that's your stomatocyte. Okay, are there any questions? Anything you want me to clarify? You'll probably want to go over this lecture again by yourself, and then if you have any questions, then make sure you ask it at the start of lecture next Wednesday. So I know I went over some processes like the iron and iron deficiency anemia, the mechanism, the bone marrow iron metabolism. Oh, I hope you got ferric versus ferrous and the met hemoglobin. I hope you understood all that. But go over the question again, and hopefully the recording worked, and I can probably save it and send it to you. So let's see if I can stop the recording.
I have a question for you.
Okay.
So for the ferritin level, it will represent how much iron is in the blood,
Iron is stored.
how much iron is stored.
Right. Remember, ferritin is stored. Iron is stored as ferritin. And then once it's stored and demand is increased, then the reticular endothelial cells will extract the iron from ferritin and give it over to transferrin to send over to the bone marrow. Okay, is that clear?
It is clear, but is there a difference in the wording with stored and held?
There, yeah, ferritin is the amount of iron is stored.
Okay,
So remember, ferritin levels estimates the amount of iron that is stored, and it's stored in the reticular endothelial system. Okay, so whenever there's a need for the iron, it's going to pluck it out from the ferritin and give it to the RE cells are going to pluck it out from the ferritin and give it to transferrin.
okay,
And the transferrin will take that iron and deliver it to the bone marrow or to wherever place it needs, like the gut, liver, or extravascular needs. Okay.
that helps. Thank you.
Okay. So ferritin, iron is stored in ferritin, and it's in the reticular endothelial cells. Anybody else? That's a good question. I know you're going to have to probably look at it. Look at, I mean, stare at this for a while, and then it'll become clear to you. So ferritin is here. Transferrin is going to take it from, it's going to take iron from here, from the ferritin and deliver it to the bone marrow. Okay.
So ferritin is like a little purse and it's holding it.
Yeah.
Okay.
Remember,
I like it.
iron cannot be in its free form. That's toxic. Okay, so
Got
it has to be bound to a protein. So here it's bound to ferritin.
Okay. Thank you.
You're welcome. Anybody else? All right, so. All right,